This project is from the ground up for absolute beginners, so we will start by installing my game engine of choice, Godot engine. Find your way to godotengine.org and click Download Latest, which for me is version 4.1. Then click the blue download button to get a hold of the engine. It works on Windows, Linux, Mac, and more recently on mobile too. Once you have unzipped that download, open Godot and select New Project from the Project Manager window. In the project name text box, I will name the project Basic 3D Platformer. Click Create Folder and then Create and Edit. Now we are in the editor proper, I will take a moment to cover the key areas we will be interacting with. The top bar holds menu buttons on the left, 4 buttons for the main screens in the center, and playback controls on the right. The main screen buttons determine what is in the middle of our display. By default, in 3D mode, this will be our viewport showing us the game world. On the left are 2 docks, the scene tree showing virtual objects in our game, and the file system for accessing resources like images, sound files, and the like. On the right is another dock containing the inspector. This is where we will configure our game objects. Now we are in the game engine proper, we can get our starting 3D scene set up. We need 3 things to be able to see our game world in action: a camera, a world environment, and a light source. Create a new 3D scene by selecting the 3D scene option from the scene tree dock. This node 3D is the root of our scene, and we can add more nodes as children of it. Click the plus icon at the top of the screen to create a new node, or use the shortcut Ctrl and A. Type Camera 3D into the search bar at the top of the Create New Node window, and click on the Camera 3D node from the list below and click the Create button to add this new Camera 3D to our scene. This camera allows us to see the game world when we run the game, but at the moment there is nothing in it to display, so we need to add a world environment and a light. At the top of the viewport, there is a toolbar with buttons for previewing our game world. Select the button with 3 vertical dots. This opens a menu for adding preview environments to the scene. Click the Add Sun to Scene and Add Environment to Scene buttons to add the default world environment and directional light 3D to the scene. You can customize colors and light angles with the options in this menu. Now we can get our scene running in real time. In the top bar on the far right, you will see 6 buttons that are all playback controls. Click the Run Current Scene button, which looks like a play button on a clipboard. Godot will then prompt you to save the scene if you haven't already. I will name the scene level.scene in the file prompt at the bottom, and click Save. A window will open with our game running, and this will look like the viewport in the Godot editor itself, just showing the procedural sky we added in our world environment as viewed from the perspective of this new camera. Now is a good time to add a floor to give us something to look at and get used to orienting objects like the camera. To act as a floor, we need to add a Mesh Instance 3D to our scene. When you add a node to the scene, it is added as a child of whatever node is selected in the scene tree. Left-click on the node 3D to select it. Selected nodes are highlighted with a pale blue rectangle. With the node 3D selected, open the Create New Node dialog. As you might be able to remember, we can either use the plus or we can use the shortcut Ctrl and A. In the search bar, find and select Mesh Instance 3D, then click Create. This Mesh Instance 3D node is our essential tool for showing simple 3D shapes. In the scene tree on the left, you should see the mesh instance is now selected with the light blue highlight. If not, select the Mesh Instance 3D by left-clicking on it. When a node is selected in the scene tree, we can access their properties in the inspector on the right. In the inspector, the Mesh Instance 3D node has a mesh property, where we can select how it should look from a variety of primitive shapes, like box, sphere, and cylinder. To select a mesh for this Mesh Instance 3D, click on the word empty next to the word mesh. Then select New Plane Mesh from this list to create our floor mesh. This plane is then visible in the editor's viewport as a 2 meter by 2 meter grey square. The plane is only visible from above, as a plane mesh is a one-sided object. If you move the mouse over the viewport, you can control the view with a variety of gestures. Click and hold the middle mouse button and drag the mouse up, and your view will rotate down to a view below the floor, showing it is transparent from the other side. Click and hold the middle mouse button and drag the mouse down to rotate the view back up, and you can see the floor again. The floor is too small at the moment, so we're going to need to update its size in the inspector. The mesh property of the mesh instance 3D now holds a plane mesh object that we can customize. If you click on the picture of a plane, the object will expand and we can customize its properties in the inspector. Godot has objects we can expand like this, as not all meshes will have the same properties. This plane mesh only has a width and a height, but if we say had a box mesh, it would also have a depth property. We can set the floor size with the mesh's size property. Set the size property's X and Y values to 10 meters by 10 meters. You will see the mesh updates in real time in the viewport. While hovering the mouse over the viewport, you can scroll the mouse wheel up and down to zoom the camera in and out for a better view. Now we need to move our camera 3D node for a better view. If we run the scene as it is, we will not be able to see anything because the camera is inside the floor. If you ever quickly want to check what the camera 3D can see, select the camera in the scene tree and hit Ctrl-P to toggle the camera preview. This will show what the camera can see directly in the viewport. You can also toggle this view with the preview check mark in the top left of the viewport. To update the camera's position and orientation, we can use the 3D gizmo. This is a handy tool available directly in the viewport for whatever node we have selected in the scene tree. Select the camera 3D node in the scene tree so we can update it with the gizmo. The gizmo is the 3 arrows and circular arcs in green, blue and red in the viewport. The gizmo is centered on our camera, which is made visible as a small purple pyramid with a square base indicating the direction the camera is pointing. If you hover your mouse over the tips of the arrow on the gizmo, the arrow will change to white. This indicates you can drag the whole node in that direction by clicking the left mouse button and dragging. The motion is locked in the axis of the arrow. Click the green arrow and drag the camera upwards. If anything happens you don't expect, the editor supports using Ctrl-Z and Ctrl-Shift-Z to undo and redo actions. We can now use that preview toggle to see what the camera can see from its current position. The grey floor should be visible at the bottom of the screen. This gizmo updates the position and rotation property that all 3D nodes have. We can update those values manually in the inspector. Find the Node 3D section and expand the Transform dropdown. You should see the position's Y property is something other than 0 as you changed its position with the gizmo. I will manually set the camera's height to 2 meters up by selecting the Y value in the position property and entering 2. Now when running the current scene with F6 or the play current scene button, you should see the same thing I do here. Godot offers many powerful graphical options to control the appearance of what you create, and it is best to understand these settings early so you can fix graphical problems as you encounter them. In the top bar on the left, select the Project drop-down, and from that drop-down list, click on Project Settings. The Project Settings window holds a host of powerful options for your games, as well as a bunch of useful customizations. In the tree on the left, you will see a variety of tabs for options relating to your project. Under the Display drop-down, click on the Window button, and options relating to your game window will open on the right side of the page. I am using a 1920 by 1080 monitor, so to best fit, I'm going to set my viewport width and heights to the same dimensions. I also want my game to take up the full screen and leave the mouse free to close the window, so I'm going to change the mode to maximized. The stretch mode and resizable options on the screen are often important in letting you make the screen have fixed dimensions and stretching pixels to keep the viewport scale the same on different monitors. The next important setting to cover is anti-aliasing options. Under the Rendering subheading, you can find and select the Anti-aliasing tab. Anti-aliasing options help us avoid jagged, sharp contrast edges in our games. These options are all disabled by default for the best performance. Hovering over the names of options like MSA 3D will reveal a tooltip giving you more detail about the option. I'm going to set the multi-sample anti-aliasing MSAA 3D to 2 times. To keep this window streamlined, Godot 4 added an advanced settings toggle in the top right. Clicking on this toggle will reveal many more project settings that are worth scrolling through and investigating at your own leisure. Click on the toggle and scroll down to Lights and Shadows, under the Rendering dropdown. Here we can control the quality of our shadows. For the moment, we only care about the directional shadow section, as that covers the sun we added earlier, and we don't have any other lights. Click on the drop-down for soft shadow filter quality, and you'll see a whole host of options. I will slightly improve the quality by changing the quality to soft medium. We are now 1/3 of the way through my guide on how to create a 3D platformer in Godot 4.1. This is all part of the free supplement in my course Godot for Beginners. If you head on over to itch, there's a link down there, you will be able to go ahead and download these 3 sections all in written form so that you can follow along with that if you find that a more helpful way of learning. Once that's all wrapped up, there are 7 more sections available covering a bunch of extra topics relevant to 3D platformers, such as transitioning between levels, making grid maps, particles, and the like, all available in my course Godot for Beginners, and I'm considering creating more video content like this to go ahead and cover those topics in the future. Anyway, I'll let you get back to the rest of the video. Okay, have fun. Now we have a simple level, we can focus on getting our player character up and running. We may want to add the player to a variety of levels like this one, so we will make the player its own scene. In the top bar on the left, click the Scene drop-down and select New Scene. In the new window in the scene tree, select the Other Node option. When you select the Other Node option, the Create New Node dialog opens and lets us select any node to be the root of our scene. For our player character, 2 nodes are up for consideration: Rigid Body 3D and Character Body 3D. I am going to show you how to make a Rigid Body 3D player character. This is physics-based at the cost of less precise control than the kinematic counterpart. In the search bar, find Rigid Body 3D, select it, and click Create. Now we can see our Rigid Body 3D in the scene tree. Double-click on the node and rename it to Player, then hit Enter. When you create a body node in Godot, to make them interact with other nodes and the physics of the engine, we need 2 things: a mesh, so we can see the body, and a collision shape 3D. Add a mesh instance 3D as a child of the Rigid Body 3D we named Player. This node is how we will see our player. With the mesh instance 3D selected in the scene tree, look to the inspector on the right. Click the Mesh property drop-down and select New Capsule Mesh from the list. When you have a mesh instance 3D, you often will want to create a matching collision shape. To help with this, there is a contextual mesh drop-down at the top of the viewport we can use to generate a collision shape 3D. With the mesh instance 3D selected, click the Mesh button at the top middle of the viewport. Then, from the drop-down, select Create Simplified Convex Collision Sibling. Now we have our collision shape, we can focus on setting up our Rigid Body 3D for use as a player character. Select the Rigid Body 3D player in the scene tree, and in the inspector, find the lock rotation property and enable it. Rigid bodies are often used as physics objects, with great freedom of movement and rotation. We need to lock our player's rotation so the capsule does not tip over as our player walks around. Godot uses script files to give instructions to the objects in our games. We write these in the GD script language, a specialized lightweight scripting language. We will add a script to our player character that will listen to key presses and use those to move the player in the corresponding direction. Right-click on the Rigid Body 3D root of our scene, and from the drop-down menu, select the Attach Script option, which is an icon of a little scroll of paper and a green plus. This will open a contextual window for creating a script file. We do not need to customize any of these options, so just click Create. This will change our main screen for the first time. Instead of seeing the 3D viewport as usual, we can now see the script screen. You can swap back and forth between these screens by clicking on the 3D button or the script button in the middle of the top bar as you need them. Our script has a few lines that are important to us right now. The first lines of the script says extend, then the name of the node, in our case, extends Rigid Body 3D. This tells us the script is attached to a Rigid Body 3D node, and we can access all the properties and functions of a Rigid Body 3D in code. Two functions have been added to this script by default. The functions are defined with the keyword func, followed by their names and parentheses. We will be focusing on the process virtual function. Godot has a bunch of virtual functions. A virtual function is a kind of built-in function you can add for a specific task. They have a specific name and specific parameters. Process is a virtual function. It runs every frame, so usually 60 times per second. This makes it an effective way to update your game in real time. The delta parameter tells us how many seconds it has been since the last frame, which is necessary for making changes appear the same on different machines, no matter how fast the game is running. Functions use indentation to separate code into blocks, so the pass keyword is indented to show it is inside the process function. The pass keyword indicates we do not want to do anything in this function. You are not allowed to leave a function empty, so pass is often used as a placeholder. In the process function, we can listen to input from the user, and if the forward button is pressed, move the player character forwards. Input is a global script you can access from anywhere. UI up is an event for the up arrow key. If this up button is pressed, the getActionStrength function gives us a value of 1.0. Otherwise, it returns 0.0 and the player will not move. So now our variable input is either 1.0 if the up arrow is pressed, or 0.0 if it isn't. Apply central force is a function of the Rigid Body 3D itself. It lets us apply a force in a 3D direction. 3D directions are represented by the vector3 object, and vector3.forward gives us a vector3 pointing forwards. The asterisk symbol means we are multiplying the velocity by the 1200.0 that comes after. This makes the force we apply larger, so the player will move further forwards when the button is pressed. We need to multiply the force by delta to avoid issues on machines with different frame rates. When the button is not pressed, multiplying the direction by 0.0 will give us no velocity. This force applies every frame, and combined with the mass of our rigid body 3D, gives us a forward velocity when the up arrow is held. To test this script, we need to save the scene. In the top bar, click the Scene drop-down and select Save Scene. The Save Scene As prompt should automatically name the file what our root node is called, player.scene. Click Save. This player is now a scene we can see down in the scene tree. Double-click on level.scene in the scene tree to reopen that scene. Then, in the top bar, click the 3D main screen button to return our view to 3D. Now we can add the player scene to the level. Click on the root of the level scene in the scene tree to select it. Right-click on player.scene down in the File system and select Instantiate from the drop-down menu. Instantiating a scene creates a copy of that scene as a child of the currently selected node. Now the player will be visible in the level, but there are a few things we need to clean up before we can start running the scene. First, our player is clipping through the floor in the middle of the viewport. This makes sense as the player's center is in the middle of their Mesh Instance 3D, so we need to raise the player up. Select the player node, and in the inspector, find the Transform section and expand it. Set the position's Y value to 2 to raise the player above the floor and the Z value to -2, so the player is in front of the camera. If we run the scene now, our player will fall straight through the floor. This is because our floor is just a mesh and not a physics body like the player. In the level scene, select the Floor Mesh Instance 3D, then at the top of the viewport, click the Mesh Context button and select Create Trimesh Static Body from the drop-down menu. This creates a static body 3D as a child of the Mesh Instance 3D, with a collision shape matching the mesh itself. A static body 3D is another kind of physics body Godot uses that is intended for objects that do not move. Now, if we run the scene with the Play Current Scene button in the top bar, when the game runs, the player will fall to the floor and stay there. If we push the up arrow on the keyboard, the player should then hurl themselves off of the platform. Most modern games do not use arrow keys for movement, instead opting for the W, A, S, and D keys. To set this up, we need to configure input events for the project. Godot lets you access every input the user makes, but for convenience, multiple input device support, and to easier group events, you can use the input map, which lets you mark a specific event with a name. You can even make multiple inputs trigger the same event, for example, both the spacebar and A button on controllers triggering a jump. In the top bar, click the Project drop-down and select Project Settings. Then at the top of the Project Settings window, click the Input Map tab. The UI up event we listen to for movement is defined here, but is hidden by default. Click the Show Built-in Actions toggle to see all the predefined actions you can listen to. In the Add New Action bar at the top, type move_forward and hit Enter, or click the Add button. This creates an input event called Move Forward that we can attach inputs to. On the right of the Move Forward input event, click the plus button to open the event configuration window. In this window, you can either select the input you want from the drop-down menus or push the actual input for the event you want. If you push the W key, the panel will update to show the W key, and that it detected a physical key press. Click OK to confirm this is the input you want, and now whenever the W key is pressed in-game, the move forward event will trigger, which we can look up by name. Repeat the process for move left with the A key, move right with the D key, and move back with the S key. You can now close the project settings window and return to the script screen. Return to the script view by clicking the script button in the middle of the top bar. In our process function, we now want our script to listen to all 4 inputs instead of just forwards. Delete the contents of the process function and replace it with the following. We create a variable called input and tell Godot it is a vector 3 containing the 3 directions the player can move: left and right on the x-axis, up and down on the y-axis, forward and back on the z-axis. Adding movement like this is a common task in Godot, so there is a helpful function built in, the getAxis function. This function returns -1.0 if the first input event is detected, 1.0 if the second input event is detected, and 0.0 if neither or both events are detected. So, for the line input.x equals input.getAxis move left, move right, this code sets the x value of our 3D vector to 1.0 when we press the D key, or -1.0 if we press the A key, otherwise leaving it at 0.0 if neither or both are pressed. After we get both of those axes, we are left with a vector 3 that can move our player in 3D space when they push the W, A, S, or D keys. Running the level scene now will let you move the player around on the little platform. You may notice the movement is a little floaty. We can rectify this easily. Head back to the editor. Select the player in the scene tree and look in the inspector. Under the linear drop-down, find the damp option and set it to 3. Now, the player will lose velocity as they move, to linear damping. The higher this number is, the more forces will dampen. In third-person games, the camera is typically attached to the player and pivots around a point on them to keep the player in frame. Typically, a node's position is relative to its parent. This means if we add a camera 3D as a child of the player, it will move with them, and if the player rotates, so will the camera. Godot does let you ignore relative positioning with a special property called Set as Top Level you can enable on any Node 3D. To get the camera setup we want, I am going to use nodes that will act as pivots. Then we can rotate those pivots to control the camera angle with precision. Open the player scene and change the main screen to the 3D view. Select the player root node and we can add our first pivot. Create a new node 3D by clicking the Create New Node Plus icon at the top of the scene tree and searching for it. When the node 3D is created, double-click on it in the scene tree and rename it to Twist Pivot. This is currently a point in 3D space in the middle of our character that the camera can rotate around horizontally. We need a second pivot that will let us tilt our camera up and down. Add another new node 3D as a child of the Twist Pivot and rename it to Pitch Pivot. The node 3D is the simplest form of 3D node available to us. It just has a transform property and options for visibility, so we can position it in 3D space and rotate it. Perfect for the pivoting action we need. With the pitch pivot selected, create a new camera 3D node as a child. We can now move this camera straight back from the pitch pivot, so it's effectively on a long camera arm rotating around the center of the player. With the camera 3D selected, look over to the inspector. Under the Transform drop-down, set its position's Z value to 3 meters. This is all we need to get the camera centered on the player. Save our changes in this scene with Ctrl+S. Return to level.scene and delete the old stationary camera 3D node with the delete key. Now, when you run the level, our camera will follow the player as we move around the platform. Usually, in third-person games, the center of the screen is an area ahead of the player your view can focus on, with the player character lower down. We can fiddle with the position properties of our pivot to achieve that perspective. Go back to the player scene and select the camera 3D. Change the view to preview mode with the Ctrl+P hotkey or the preview toggle in the top left of the viewport. Now we can see the camera's perspective, we can fiddle with the transformations of our pivots. Select the twist pivot in the scene tree, then in the inspector, find the position property and set the Y value to 1.0. You'll see the camera's view is 1 meter higher. Now we can orient the pitch pivot so the focus is closer to the floor rather than straight ahead. Find the rotation property in the inspector and set the X value to -10 degrees. This will angle the camera down towards the floor in the middle distance. Press Ctrl+P or the preview toggle again to return the view to the free camera in the viewport. Now we can return to the level and run the scene to get a feel for this new camera setup. You have a lot of flexibility with this camera position. You can opt for over-the-shoulder views, move the player camera further away, closer, angled more towards the floor, all with the rotation and positions of these 2 pivots. Now we can focus on getting input from the mouse to twist the twist pivot and pitch the pitch pivot. To best listen to mouse input, we should set the mouse mode to captured. Godot has a variety of mouse modes for different situations. By default, our mouse is free, meaning the mouse is both visible and nothing is controlling its position. We want to change the mode to captured, so the mouse is invisible and unable to leave our game window. Change the main screen back to the script view, and we are going to add some code to another function. Add the following ready function. The _ready function runs whenever the node first loads, so unlike the process function that runs every frame, the ready function will run only once. Here we can inform the engine that we should change the mouse mode to be captured. However, as it stands, this is awkward for us to test, as we cannot close the window with the mouse anymore. We need to add a way to free the mouse in-game. In the process function, add the following code. As the process function runs every frame, we can listen for when the UI cancel event occurs. This is a built-in event that emits when the escape key is pressed. The if statement checks if a condition is true. If so, the indented code block will run. So, if the escape key is pressed, this script changes the mouse mode back to visible, so the mouse is free. When we run the level scene, you should see the mouse disappear as the window opens, but when you press the escape key, it becomes visible again. Now our mouse is hidden, we can move on to getting information about the direction our mouse is moving. Whenever we move the mouse, an event emits like when button keys are pressed. Events can be one of many types: regular button presses, mouse button presses, or in this case, mouse motion. We are going to add the unhandled input function to our player script, one of Godot's virtual functions for handling inputs. First, at the top of the script, just after the extends keyword, define 3 variables. We are going to share these between multiple functions, so they need to be defined outside of the functions we have already written. When you define a variable in Godot, You can either define it with the equals symbol or with a colon followed by the equals symbol. When you add the colon, Godot will keep a track of what kind of value the variable is holding. This will give you better code completion and makes your scripts run a little bit faster. In this case, we are letting Godot know that those three variables will hold numbers with a decimal place, which is known as a float value. These variables are going to be responsible for a few things. Mouse sensitivity controls the speed our camera should rotate proportionally to the mouse input. Twist input stores how much our mouse has moved horizontally every frame, and pitch input stores how much our mouse has moved vertically every frame. Now we can add the unhandled input function. Where it is added in the script isn't important, but I'm adding it after the process function. This is the largest block of code we've looked at so far, so let's assess it line by line. Func unhandled input event. This virtual function will run every time an event is detected that has not already been handled by another script. There are a variety of events that the event parameter can be. We could receive an input event mouse button, an input event joypad button, an input event mouse motion, and more. Different events hold different data, so we will need to check what kind of event the function has received. If event is input event mouse motion. If the event is mouse motion, we will always be updated when the player moves the mouse around. These events tell us how far the mouse has moved from its last position. If input.getMouseMode is captured. Checking if the mouse mode is captured means when we press escape to free our mouse from the game, our mouse inputs will be ignored and the camera will no longer move around. This is useful for preventing camera movement when the mouse is free, like when the player opens a menu. Twist input equals negative event.relative.x times mouse sensitivity, and the same for pitch input and event.relative.y. Now we set the values for the twist input and pitch input variables we defined at the top of the script. Event.relative stores how far the mouse motion is relative to its last recorded position. It has an x value storing horizontal change, and a y value storing vertical changes. We store the negative version of this value, so when we rotate the camera, it rotates in the same direction the mouse is moving. Finally, we multiply the event's relative value by the mouse sensitivity. The lower the mouse sensitivity is, the slower our camera will rotate, and the higher it is, the faster the camera will rotate. Now we have values for how far our mouse is moving, we can focus on applying these changes to our camera, and taking advantage of those pivots we created earlier. Applying rotations to 3D objects is a complicated process, with a large number of ways of representing 3D rotations on 3D objects. To avoid any confusion about how rotations should be applied to our nodes, I like having separate pivots dedicated to rotating horizontally and vertically. Return to the process function and add the following line of code at the end. If you did not rename the node 3D to twist pivot, this line of code will raise an error when the code runs. Ensure it's named correctly, your scene tree should look like mine does. The dollar symbol is shorthand for accessing nodes in the scene tree. Our player script has a child node called twist pivot, so the dollar symbol lets us access that node with the given name. When you have access to a node like this, you can do many things. Save it to a variable, access its properties, call its functions, like QFree to delete it. 3D nodes have functions for altering their transform property. We are going to use those rotate functions to rotate our camera around the pivots. The rotate Y function rotates the camera around the Y-axis by the number of radians given as a parameter. Radians are a unit for measuring angles like degrees, where instead of a complete rotation being represented by 360 degrees, it's represented by 2 pi. This script rotates our twist pivot left and right according to how far the mouse has moved horizontally. If we return to the level scene and run the game, we should see that when we move the mouse, the camera rotates around the player. To avoid the need to keep changing scenes when running the game, you can set a main scene. Running a scene with F5 or the big play button will let you select the current scene as the main scene of your game. After selecting the scene, the F5 key and big play button will always launch that selected scene. If you want to alter the main scene later on, you can access it in Project Settings. We have mouse motion working horizontally, but there is a complication if we add vertical mouse motion. If you spin the camera all the way up or down, eventually the camera will turn upside down. To avoid this, we need to limit how much the pitch pivot can rotate. Add these extra lines to the process function. As with the twist pivot, this path will cause a crash if the second pivot is not called pitch pivot. If you want to find out what a path should be, Godot can generate it for you. In the scene tree, right-click on the node you want a path to, and select the Copy Node Path option. For this code block, we start in the same way as the twist pivot. We get access to the pitch pivot and call its rotateX function, and pass in the pitch input holding the mouse's vertical motion. After we have rotated the pivot around the x-axis, we need to limit how far the pivot can rotate. The rotation property stores the rotation of the node in radians for the x, y, and z axis. We access its x value and set it to the result of the clamp function. Clamp is a particularly useful built-in function that takes 3 parameters: the input you want to modify, the minimum possible value you want that input to have, and the maximum possible value you want that input to have. Whenever the input goes below the lowest value we want, clamp returns our lower boundary, and if our input goes above the higher boundary, clamp returns the higher boundary. This makes it a helpful function for keeping a value between boundaries. In our case, we keep the rotation on the x-axis less than 0.5 radians and above negative 0.5 radians. This makes it so our player cannot tilt the camera above or below about 30 degrees. Finally, we set the twist input and pitch input to 0. If we did not, the camera would continuously move in the last direction you moved the mouse. This way, the camera moves as far as the mouse moved, then stops. And with that, you can run the scene and look around with the mouse. But there are a few changes we can make to our code to make it easier to read. You will notice that the arguments for the clamp function are spread out over multiple lines. Because they are indented, Godot understands that they are all parameters, but it needs this much space because the definition of pitch pivot is so long. We can get around these long paths by assigning the nodes to shorter variable names. At the top of the script, where the 3 variables for pitch input and the like are defined, add the following. Using the @ symbol in this way is a new syntax specific to Godot 4. It is the first character for a specific kind of keyword called an annotation. The annotation onReady indicates that the variable is related to a node in the scene tree. Just before the script's ready function is called, the onReady variables are evaluated. As a result, we can use these variables in our ready function. There are a host of other annotations that you can explore thanks to code completion. Once you type the @ symbol into the code editor, a drop-down will reveal the list of all the available annotations starting with the @ symbol. Now we have two variables referring to our pivots, we can replace the long paths in our camera rotation code block with those new names. Our clamp function currently handles its maximum and minimum angles for the camera in radians, but this is not easy for most people, with degrees being a more common unit. Godot has built-in functions for converting values from degrees to radians and vice versa. The deg to rad function converts a parameter from degrees into radians. The rad to deg function converts a parameter from radians into degrees. We can replace the negative and positive 0.5 boundary with the deg to rad function, and a value in degrees as a parameter. Replace the clamp function with the following. The camera moves around with the mouse, but if you move the player, you will quickly find the player does not move in the direction the camera is facing. When the W key is pressed, the player always moves in the global forward direction, which is -Z. To fix this, instead of moving the player globally forward when the W key is pressed, we need to move the player forward from the camera's perspective. 3D objects in Godot have a transform property. This stores two things: the object's position in 3D space, and the object's basis, which tells us its rotation and scale. By storing the way we want to move the player as a vector 3, we can combine it with the camera's basis to rotate the force to the same way as the camera. Handling basis and 3D rotations is a complex process. Thankfully, the actual steps we need to take in code are simple. Our twist pivot is rotated the same way as the camera on the y-axis, so we can use its basis. To rotate a vector 3 to be the same as a basis, you multiply the basis by the vector 3. So, we can replace the apply force function in the process function with the following line. When you multiply a basis and a vector 3, the vector's forward direction is aligned with the rotation of the basis. So our vector that points globally forwards when W is pressed will point forwards from the twist pivot's perspective. And with that, our player can look around and move relative to their orientation. Bram again. Thank you very much for watching. You've now finished the first 3 chapters of my topic, how to make a 3D platformer, in my course Godot for Beginners. If you want to follow 7 more topics covering a whole bunch of other stuff, all in written form, go and check out Godot for Beginners. It's all there. I hope that this is going to start the process of me being able to introduce some video content into the course itself as opposed to just written guides. I've had a lot of requests for if I have more video content like this. It took a lot of time to put together, and I hope you've enjoyed all of the depth I've been able to go into. If you want to support me in another way, I also have a Patreon. Thank you very much to my patrons on there. And you can help support me putting out more free content like this. In my most recent video, I've started working on a little cooking game project. That's quite fun to check out. Please do have a look at that and see the kind of cutesy environments you can create in Godot 4. The course is going to be on sale, big one, 40% off for the first 2 weeks that this video is out. Okay. Thanks so much for watching, and I will see you in the next one.